Welcome. Today, we're going to unravel a classic physics puzzle that honestly feels like it shouldn't be possible, the tug of war. All right, let's get right into it. This one's a real head scratcher, right? I mean, if both teams are yanking on that rope with the exact same force, just in opposite directions, how does anyone ever win? Shouldn't it just be a permanent standstill? So, to crack this paradox, we've got to build a little toolkit. We need to understand the basic rules of how things move. And it all kicks off with one super fundamental idea. Okay, so what is a force? In physics, it's not some fuzzy concept of strength. It's way more specific. It's a push or a pull. Simple as that. But here's the kicker. It always acts between two objects. You can't have a force all by itself. Think about it. Your hand pushing a box, gravity pulling an apple down. It's always an interaction. And what do forces do? Well, they're the agents of change. A force can get something moving, stop it in its tracks, or even bend it out of shape. You know, like when you see a heavy barbell start to flex, that's force at work. You could say forces are the engine that drives all motion in the universe. Now, here's something that's absolutely crucial to get. Forces are what we call vectors. That's a fancy word, but all it means is that direction matters a lot. Pushing something up with 500 newtons of force is a totally different ballgame than pushing it down with the same strength. But something like mass, that's a scalar. It's just a number. You have 80 kilograms of mass, that's it. There's no 80 kilograms to the left. The direction just doesn't apply. So how do we keep track of all this? Well, physicists came up with a pretty neat trick. They just draw arrows. Seriously. The arrow starts where the force hits, it points in the direction the force is going, and a bigger force gets a longer arrow. It's a super simple way to map out what's happening. And with that little visual tool in our back pocket, we can start looking at the actual rulebook for motion. All right, we've got the basics. Now let's get to the main event, Newton's legendary rules of motion. These are the laws that Isaac Newton figured out more than 300 years ago, and they still run the show. First up, Newton's first law. You've probably heard this one as the law of inertia, and really it all comes down to one word, balance. It tells us exactly what happens when every single push and pull on an object completely cancels each other out. So what does that mean? It means an object at rest is going to stay at rest, and an object that's moving, it's going to keep moving at the same speed in the same direction. The key takeaway here is that if all the forces are balanced, there's no change. The object just keeps on keeping on. Think of a car on cruise control. The engine's push forward is perfectly balanced by the air pushing back. Okay, so balanced forces are kinda boring. Nothing changes. But what happens when the forces are unbalanced? Ah, now we're talking. That's Newton's second law, and this is where things get interesting. This law is the famous F equals ma. If you have an unbalanced force, you get acceleration. It changes in speed or direction. The more force you apply, the more acceleration you get. Makes sense, right? But here's the other side of the coin. The more massive something is, the less it accelerates for the same push. That property, that resistance to being moved, that's inertia. It's exactly why it's a nightmare to push a stalled truck, but pretty easy to push a shopping cart. Okay, we've got force, we've got vectors, we've got Newton's first two laws, we have all the pieces of the puzzle. It's time to go back to that tug of war and finally figure out what's really going on. And this brings us to the grand finale, Newton's third law. This is the one everybody knows, right? For every action, there's an equal and opposite reaction. It sounds so simple, but honestly, this is probably the most misunderstood law in all of physics. And that misunderstanding is the entire reason the tug of war problem is such a paradox. So let's apply it. The rope pulls on team A. That's the action. So the rope must also pull on team B with an equal and opposite force. The forces are a perfect pair. They have to be. So the paradox is totally real. If the pulls on each team from the rope are identical, winning can't have anything to do with pulling harder on the rope. The secret has to be somewhere else. And here's the big misconception, the mistake almost everyone makes. We've been staring at the rope this whole time, but the secret to winning tug of war isn't on the rope. It's not about the rope at all. It's about how the teams are interacting with something else entirely, the ground. Okay, let's zoom in and just look at one of the teams. Forget the other one for a second. What forces are acting on, say, the winning team? Well, you've got the rope pulling them backward, but then you've got the ground, and the ground is pushing them forward. And that is the secret. That's the whole shebang right there. You don't win tug of war by pulling harder on the rope. We already know that's impossible. Newton's third law says so. No, you win by pushing harder on the ground. Okay, let's walk through this. The winning team plants their feet and they push backwards on the ground. That's the action. What's the reaction? According to Newton's third law, the ground pushes forwards on their feet with an equal and opposite force. We call that force friction. Now, if that forward push from the ground is bigger than the backward pull from the rope, what do we have? An unbalanced force. And what does an unbalanced force cause? Acceleration. They start moving and they win the game. The real contest isn't team versus team, it's team versus planet Earth. And just like that, the paradox is solved. It was never about the force in the rope. It was always about the winning team being able to generate a bigger external force from the ground. They create a net forward force, and that's what gets them moving. So I'll leave you with one last thing to chew on. Picture an astronaut in space. They push on the massive International Space Station. Now, according to Newton's third law, the force the astronaut puts on the station is exactly the same as the force the station puts on the astronaut. So why does the astronaut go flying backwards while the station barely budges? The clue is back in Newton's second law. Think about it. Thanks for joining this explainer.